Perhaps on first sight of this classic formation, stepping as it were out of the sea, we can imagine how tempting it was to think, as did some early geologists known as Neptunists, that these rocks had a marine origin. But this is evidently not the case for the rock composing the Giant's Causeway in County Antrim, Northern Ireland. Let's take a closer look and see if we can discover some of the reasons why. The vertical columns and the horizontal cracks indicate that this could be some sort of a lava flow. The main joints have developed perpendicular to the cooling surfaces. And it may appear that the lava flow is dipping towards the left, but this isn't the case. It's simply an erosion feature brought about by the sea. Contraction of the lava flow as it collected has caused these hexagonal columns to form on cooling. Further cooling and shrinkage has formed these interesting convex and concave surfaces. Some of the columns are hexagonal, others are seven-sided, five-sided, or even four-sided. We call this polygonal jointing. We're not able to hammer here to get a fresh piece of rock because it's a protected site, but there are plenty of fresh surfaces that we can look at. There's still not very much to see, so we really need to look at a thin section. This shows a rock with a finely crystalline texture. The crystals are interlocking with random orientation, indicating an igneous rock which cooled fairly quickly. Between crossed polars, it contains small crystals of twinned plagioclase feldspar with first-order interference colours, together with mafic minerals such as olivine and pyroxene, though these are less obvious because they've been altered. Looking at the thin section confirms that this is in fact a basalt, but there are other clues that we can look for. East of the causeway, one other feature that takes the eye is a very distinctive red band that occurs between the two sets of lava flows. So let's go there and find out what it is.
I'm now at the level of the red horizon, and from close up on the path it really is quite an intriguing rock. It's yellow coloured here and quite deeply red coloured here. There's actually a lot of colour variation within it, but there are also some grey patches as well. I can see another feature of it, that the rock itself is in fact very crumbly. What we have here is a rock that's been intensely chemically weathered. We started off with a basalt, and under what was probably humid conditions, we had two stages of alteration to this rock. The first stage involves the breakdown of feldspars, the pyroxenes, plus any olivine that's present, releasing in solution soluble ions of calcium, sodium and potassium. And it leaves behind a kaolinitic-rich rock, which is effectively a clay-rich rock. You then have a second stage, and this actually attacks in particular the silica in the rock, again removing it in solution, and leaves behind now a rock which is essentially rich in aluminium hydroxides or iron oxides in the form of bauxite or laterite. If you look at the rock, we've got this deep red weathered rock here, and we've got a purpley grey coloured rock here. The red unit is where you have more iron, and the grey unit is where you actually have more aluminium. We've just been looking at a red horizon, which locally we call the interbasaltic horizon. We know it's been developed by chemical weathering, and we suggest that the timescale over which this process operated was of the order of 10,000 years or so. Now, given the humid conditions under which this chemical weathering took place, it's not surprising that erosional processes were also operating. And in fact, in this area, a number of quite deeply incised river valleys are cut into the lava flows and the interbasaltic horizon. When you get these causeway basalts erupted, the flows flow into these valleys and fill them up. The lava, in effect, becomes ponded, so that as it starts to cool and crystallize, joint systems develop, both from the top and the base of the flow, which propagate in towards the center of the lava to generate these really quite spectacular columns. One of the features of this chemical weathering of basalts, in fact, can be seen right throughout Northern Ireland where the Antrim Plateau basalts are exposed. They frequently weather near the surface, they oxidize to a reddish colour, and that can actually produce a red coloration to the soils. Below that, there's evidence for two lava flows, and they're separated by a zone of very badly rotted basalt, which is now lateritized to a considerable degree. And then above that, we see the massive section of the second flow. Within this central portion of the flow, the joint systems have acted as zones of preferential weathering. The chemical weathering process has operated best along the joints, opening them out, and then has worked its way into the central portions of the basalt blocks. And as we can see, has generated a distinctive spheroidal type of weathering. And this is often called onion skin weathering. At this locality, I want to show you another feature of igneous rocks, but before we do that, I'm going to try a little experiment. When magma comes to the surface, you find that the reduction in pressure on the magma allows any volatiles present in it to start to exsolve in the form of gas bubbles. The effect of that can be, in some cases, to make the lava froth up. We're going to see if we can do the same here with a Coca-Cola bottle. The top's tightly screwed on at the moment, so the Coke's under pressure. But as I remove the top, gas is starting to bubble up towards the surface as the pressure is reduced on the Coca-Cola, and the carbon dioxide, if you like, exsolves. If we turn to the rocks themselves, here we can see the lateritic top of an older flow which has been weathered, and above it we can see a much fresher rock. And within that rock with these gas bubbles, but they're empty. But as we move down towards the base of the flow, some of the cavities are actually filled with a white mineral, which is either zeolite or calcite. We have one slight conundrum here, though, in the sense that the bubbles are at the base of the flow. As the magma is erupted onto the surface, and once it starts to cool as a lava flow, you actually start to get some gas rising towards the surface where it gets trapped. But the lava flow is moving. And what you see happening, in effect, is that as the lava flow moves forward, these early formed bubbles get brought down onto the base of the flow.
Another magma, this time an intrusion, but how do we know?
At first sight, an exposure like this can be slightly confusing. If I look at this distinctive face here, for example, this is actually a product of weathering. There are also some rather nice little patches of yellow and creamy white material that I can see in the foreground here and on the rocks here. But these are organic. They're actually encrusting the surface, and they're lichen. What I really need to look at this rock properly is a fresh surface. This is one of my favourite localities for looking at igneous rocks. It's a superb rock to study in the field. It's so coarse-grained you can see a lot of detail even with the naked eye. I can pick out white minerals, I can pick out black minerals. When I combine with the hand lens, I can see that these white minerals are long and elongated. They have a cleavage, which tells me it's almost certainly a felspar, possibly plagioclase. The black mineral is very shiny, it has some good flat cleavage planes as well, and it's probably a pyroxene. Now I can see a third mineral, a green glassy mineral. It has no cleavage, and I think it's probably olivine. In addition, there's a fourth mineral forming large patches within the rock. These are zeolite minerals that develop in cavities. As the magma cooled, gas that had exsolved created bubbles, if you like, spaces within the newly formed rock, and these are later mineralized, in this case by these white minerals here. And it's these that are largely responsible for this very distinctive lumpy texture that I've got, because on the open surface they're actually weathering away very easily and leave the pyroxene standing out to form the lumps. But if I look at the face behind me, I can see that there's a second type of rock in this body. It's slightly different, and I think we should have a look at that now. I've now lost the lumpy texture that I could see at the previous spot. It's still very coarse grained, but now it's quite even grained. On the fresh surface, the mineralogy is the same, On the weathered surface, the brown patches are actually the olivines that have been oxidized. What I'm dealing with here is a dolerite, an intrusive igneous rock. And what we've now got to consider is what type of igneous rock. The coarseness suggests it's possibly a pluton, it could be a sill or a dike. And what I really need is to identify a contact in order to determine the field relationships between this rock and the country rock.
The country rock into which the igneous rock has been intruded is only a couple of 100 metres away. These predominantly grey-coloured and layered rocks, originally sediments, predate the intrusion by more than 100 million years. At the contact, erosion by the sea has exposed only a single bed of the grey sedimentary rock overlying the dolerite, the brown weathered surface of which is only just visible in the foreground. The contact of the dolerite with the grey rock isn't flat. In places it bulges upwards, showing that the country rock was heated to the point where it started to deform plastically. And you can just make out a glassy rind at the contact itself. This is what we call a chilled margin. Just below the chilled margin, the dolerite is fine-grained. Much more like the dolerite in this thin section. Compared with the more coarsely crystalline texture in the example that Tony showed you earlier. The heat from the intrusion has altered the grey sediments. They have become brittle, and if we could hammer them, which we can't at this protected site, you would find that they'd be very hard and splintery. So some recrystallisation must have occurred, and must be associated with metamorphism at the contact with the hot doleritic magma. These sediments have developed a hornfels texture, and we have left till last the most convincing evidence that this hornfels was once a sedimentary rock. On the bedding plains we find marine fossils. They're ammonites. The concordant relationship between the bedding and the intrusion proves it's a sill, and we're looking at the top of the sill here. An aerial view of the whole sill at Portrush, exposed like this because nearly all the surrounding country rock has been eroded away. But not quite all. Just a tiny amount of the one-time sediments still remain on the other side of the sill.
In the late 18th century, this locality became world famous because certain geologists misidentified this hornfels as a basalt, and they used the ammonites to actually support the Neptunian idea that all igneous rocks were actually deposited in the sea. They'd actually missed the contact, but it took over 50 years before this theory was debunked.
Further west along the Antrim coast, there's an obvious contrast between the white rock of the cliffs with this black rock in the foreground. The black rock is a dolerite intrusion, and it's not bedding we're seeing here, but sheet jointing. On the surface of the sheets there are cooling cracks, formed when the magma solidified. In the distant cliffs you can make out bedding quite easily. These white rocks are sedimentary. Closer to the igneous intrusion, bedding is not so clear. The white rock is chalk, a type of limestone formed from the minute skeletal remains of marine organisms. The microfossils are so small that they are not easy to make out, even in a thin section. As a limestone, chalk should fizz with acid, which it does. The acid reacts with the calcium carbonate, releasing carbon dioxide. Also embedded in horizontal layers within the chalk are some black nodules. The material comprising these nodules doesn't fizz with acid, so it's not a carbonate rock. but it does break into sharp-edged fragments with a characteristic conchoidal fracture. Individual nodules which weather out from the chalk often retain a chalky coating. These nodules are almost pure silica and have come from the remains of other marine animals such as sponges. The nodules are composed of chert, commonly called flint when found in chalk like this. Now, when igneous material comes into contact with chalk, what do you expect would happen? There's a small intrusion in the cliffs behind the harbour. At the contact, a band of very pale whitish grey coloured rock extends into the chalk for 20 centimetres or so. Its slightly different appearance is best seen by comparison with a hand specimen of chalk, which is pure white in colour. If you hit it with a hammer, it sounds like a much harder rock than chalk. And it breaks like a crystalline rock. With acid it fizzes, so it's still a carbonate, although it's been recrystallised by contact with the hot igneous intrusion. We call this metamorphic rock marble, but here the contact metamorphism is very localised, as most of the country rock, the chalk, has remained unaltered.
Evidence for an explosive volcanic eruption is a rock apparently formed from the compaction of volcanic debris. For this magma to reach the surface, it had to be intruded through the crust. Initially explosive, the effect was to fragment some of the chalk, throwing the debris into the air. Close to the vent, this debris settled with minimal sorting, like a layer of dust. With clasts of chalk, some other rock fragments, there's even a fossil here, all in this kind of greenish-grey matrix. Here are some clasts of black to reddish-black basalt. It's a very chaotic rock. We've actually got a thin section of this from a sample we collected earlier.
Although the rock's very weathered and it's hard to distinguish individual minerals in the rock fragments, we can find some evidence of a remnant pyroclastic texture, with larger fragments chaotically preserved in a very fine grey matrix. In many places, the matrix consists of volcanic glass, which shows evidence of squashing and compaction. This is because the matrix was still soft and plastic as it cooled around the larger fragments. It's possible to identify the composition of some of these larger clasts. This fragment contains tiny rounded shells and resembles very closely the specimen of chalk that you have in the home kit.
And of course, the acid test for this being chalk is... and we call this a pyroclastic rock.
Before we finish with the igneous and metamorphic rock types, let's look at two more which give clues as to their origin when we find them in field situations. No bedding, irregular jointing, but no contact visible. And of course it's a very pink colour. If we look at a freshly broken surface, we can see that it contains abundant pink felspars and white felspars. Its crystalline texture and medium grain size would seem to indicate to me that it could be a microgranite. A thin section that we collected on an earlier trip confirms this. In thin section, the rock is medium-grained with a crystalline texture, and although quite weathered, it's still possible to make out fresh quartz and twinned potassium and plagioclase feldspar. Any micas present have been altered to secondary minerals. The grain size, mineralogy and texture confirm that it is indeed a microgranite. A reasonable hypothesis is that the rock was once a magma, and from extensive work on granites, we know that they cooled as intrusions at depth, only reaching the surface when exposed by uplift or erosion, or a combination of the two. But of course, igneous rocks are not the only rocks that are formed at depth.
Whilst many granites crystallise at a depth of about 5 to 10 kilometres, this rock has probably formed at much greater depth, perhaps 15 to 20 kilometres. It's still a crystalline rock, but if I was to look at it in a slice of the rock in this orientation, I'd see it's actually very different. There's quite a pronounced preferred orientation of the minerals in this rock. How do I form that? If I start with a sediment that's rich in clay minerals, like a mudstone, and subject it to an increase in temperature and pressure, what's going to happen? Well, it's going to start to recrystallise. And as it does so, if the pressure is operating in this orientation, the platy minerals, like micas and so on, will find it easier to develop in that orientation there. And so in essence, the long axes of these micas will be arranged in a parallel alignment, creating what we refer to as a foliation. It's a very characteristic feature of regionally metamorphosed rocks. There's one crucial difference between this rock and the granite though. Whereas the granite forms as a magma and crystallises in essence from a liquid, this rock is largely formed in the solid state. The end product of this rock is one which has this beautiful alignment of minerals, and I can see it here in this specimen. This very pronounced sheen is a totally diagnostic of mica schists, and on that basis that's what I'm going to call it.
Here are some more examples of mica schists as you might find them in the field. Often folded and refolded, there's good evidence of tectonic activity to be found in these ancient rocks. Now let's look at some rocks that form at the surface and comprise the third group, the sedimentary rocks.
When we look at this exposure, the first thing we notice is this very broad, flat surface. We call these bedding surfaces. Although it's now tilted, when it was originally deposited, it was laid down horizontally. And we're going to now try and show you some evidence for that.
First of all, what material is it made of? It's a fine-grained sandstone comprising a high percentage of quartz. But we can do better than that. Is it marine or desert deposition that we're dealing with here?
You're not going to be convinced by this, but what I'm seeing here is a trace fossil. It's a burrow structure. And in essence, it's a burrow structure that has been developed roughly perpendicular to this bedding surface. What you've got to imagine is an organism crawling over the surface and burrowing its way down into the sediment to create a vertical tube. When the organism leaves the burrow, sediment can be washed in and that hardens into a rock, and that's what you can see here. And of being slightly harder than the surrounding rock, it's now being weathered to stand out on the surface. There is other evidence though in this rock as well, because if I actually look at the surface, what I can see here are some skeletal fragments. This one, for example, is a crinoid columnal. All this material's broken up. And that suggests to me that this sediment was actually deposited in quite a high energy environment. And when these organisms died, all the various bits that were their skeleton gradually got broken up, moved about, and you're just literally seeing a surface that's covered in debris at the moment.
When you arrive at a new locality, the first thing you should do is to stand back and take a good look around.
Although there's no obvious bedding at this point, there is plenty of evidence in this rock to suggest I'm dealing with a sedimentary rock. If we look here, for example, I've got these very large clasts which are in excess of 20 centimetres, ranging down to about 2 or 3 centimetres. And most of them are showing beautifully rounded edges. This large boulder here, for example, and I can see the same thing here and here. Most of these pebbles and boulders are actually in contact with one another, for example here and here. This kind of texture we would call grain support. And in between these clasts we can actually see other material. It's much finer, but it's still in its own sense quite coarse, and I would actually call this a sand. The suggestion here is of material that's actually filtered down in between the grains to form a matrix. And it worked. The balls in the bucket were effectively the pebbles and boulders that you can see in the face here. The sand that I poured into the bucket is the material which we can see here forming the matrix between the boulders. And what in effect has happened is, as you have a high energy environment here where presumably water, the sediment was largely being carried as bed load. The boulders and pebbles being larger were probably deposited first, and as the energy waned in the flow, the finer grained sediment was deposited on top of it. But because of the large spaces between the boulders, there was plenty of room for that material to actually filter down, to form in effect a matrix. And of course eventually the whole thing lithified into the rock that we can see here today. Although the clasts in this rock are rather poorly sorted, when we look at it in terms of composition, we see that the overwhelming majority of the pebbles and boulders in this rock are actually of the same type. We have this grey, slightly crystalline rock here, quite fine grained, which I think is probably a quartzite. And there are similar examples, although they're red stained, and we can see this very shiny crystalline surface to the rock. And again, this is another example of quartzite. Both the red stained pebbles and the red stained matrix suggest to me that we've had a certain amount of oxidation here. If we think in terms of what type of rock we're dealing with, clearly it's a very coarse grained rock. If these clasts were angular, I think we would refer to this as a breccia, but here, because of the rounding of the grains, I'm going to call this a conglomerate. At this locality, it's not all conglomerate. I can see here a very different type of rock. It's showing layering. It's quite coarse to the touch, and it suggests to me that I'm dealing here with a sandstone. And when I move around the outcrop, I can see that there are some quite considerable features of interest within it. Here, for example, I can see a very sharp truncation which downfolds into the rock. When I look closely at this locality, the layers within this sandstone unit have in fact been deformed downwards. This unit has actually sunk into the sand because of its higher density, and that is what's deformed it here. What that tells me is that I've got two things. First of all, the variation in grain size between the conglomerate to the sandstone tells me I'm dealing with bedding. Secondly, the fact that the bedding surfaces here have downfolded at this point tells me that I've also got a way up structure. This must be the base of the sandstone, and this is the top of the sandstone. And therefore, if I think of this as an original sedimentary unit that was presumably deposited reasonably horizontally, it was actually laid down in a layer like this and has now been tilted in that direction.
So how might these rocks have been formed? The rounded, tumbled nature and the large size of the clasts suggests that quite a strong water current was involved, or that these pebbles were carried by a fast-flowing river some distance from the source.
The coarse grain size in both the conglomerate and the sandstone indicates that this is bed load transport, but with two contrasting energy levels. The pebbly conglomerates are a high energy event associated almost certainly with flooding. And you can pick that out with the quite sharp junctions between the sandstones and the conglomeratic units. But as the flood subsides, we see a decline in energy levels, and the end of the stage is with the finer grained sediment being deposited as a sandstone unit.
Let's wander over a succession of rocks as we might find them in the field and make some general observations about the different types we come across.
Looking at this structure here, I've got two very pronounced sets of joints that I can see. The dominant set running down the centre produces almost a channel in the middle of this structure. And perpendicular to those on the edge of the structure, I've got a number of these joints that are running across the body. If I look at this rock in hand specimen, it's crystalline, it's non-foliated, which suggests to me I'm dealing with an igneous rock. It's quite dark in colour. It's got a high mafic content, and that would suggest it's basaltic in type. But I'd need a thin section to be absolutely sure. It does give me a clue, though, as to the origin of these joints. They're almost certainly cooling joints developed within the magma. To imagine what we're seeing here, let's think of a wall that's extending a couple of kilometres out into the sea and a couple of kilometres into the land. It's a dike, an igneous intrusion that's been injected into the crust as a linear feature, discordant with the bedding on either side of it. In addition to being able to identify it as an igneous rock, we can also tell something of the age relationship. For the igneous rock to inject into the crust, the sediments must be there. And therefore, this dike has to be younger than the rocks into which it's intruded.
Now let's look at the rocks into which the dike was intruded. They're eroded by the sea, but you can still get a sense of bedding. The topmost unit is a very coarse sandstone with angular grains of quartz, some of which are up to 1 centimetre in diameter. Beneath that, a coarse sandstone, and beneath that, a finer sandstone. At the very base is a fine-grained siltstone. We often find sandstones of varying grain size and siltstones interbedded, indicating changes in depositional environments.
Look at the junction at the base of the coarse sandstone. The erosive nature of this junction is shown by the way the base of the sandstone cuts down through the underlying layers. Whereas in the conglomerate we inferred a channel deposit, here we can actually see the channel itself.
Nearby, we find a few more rock types. Notice the bedding, a clue that we're still dealing with sedimentary rocks. Let's look for some other clues.
These rocks are clearly very well bedded, but the problem I'm having here is that they're extremely weathered on the surface, and I'm finding it difficult to identify exactly what these rocks are. The only thing I can do is to try and get a fresh surface, and there's only one way I can do that. This is now a beautiful grey, fresh surface. It's glinting with skeletal material showing. There's a very obvious test I can do here. I'm going to use acid to see if there's a reaction. And oh yeah, it's fizzing like fury. Oh, this is a limestone without any doubt.
Sometimes the relationship between two lithologies is very instructive. Here, for example, is a sandstone overlain by a black rock, which I'm sure you'll easily recognise. It's a coal, ironically preserved because of the seawall that's been built on top of it. Coals typically form as an accumulation of plant material. In the underlying sandstone, we have evidence of plant rootlets. And the sandstone is rich in organic matter, which ends up as black carbonaceous material. Within the space of 200 metres, we've seen a sandstone, a siltstone, a limestone bed and a coal, a fascinating succession of different depositional environments.
Clearly, for the most part, these sediments were deposited on land. The coals, the sandstones with their channel structures and rootlet beds all support this idea. But the limestone contains fossils that indicate it was marine. To put these two ideas together, one plausible hypothesis is that we're dealing with a delta system, which was occasionally inundated by the sea.
And then 200 million years later, igneous activity and the vertical intrusion of a dike. And if we glance behind at the huge cliffs of Fair Head, we can see the horizontal intrusion of a rather large sill.
So clearly working in the field is very good. We can get a lot of experience from actually examining rocks, not just in terms of describing them, but more importantly in terms of being able to identify field relationships between one rock and other rocks in the sequence. It's all part of what we geologists refer to as getting your eye in,